Ladies and gentlemen, good morning. Welcome to the webinar on Advanced in Predictive Maintenance and System Safety Assessment, organized by CAiRS, Center for Advanced in Reliability and Safety. I'm Dr. Rainbow Lee, MC of the webinar. The webinar today has a professional program to be delivered by local and overseas professional experts and renowned industrialists. We much look forward to their sharing on their industrial and research experience. We are very honored to have 4 guest speakers this morning. They are the first one, Dr. Michael Azarian. He is a research scientist at the Center for Advanced Life Cycle Engineering of UMD. The second one is Mr. Farin Kamani. He is a PhD student in reliability engineering from UMD. The third one is Dr. Dhanada Mishra. He is the Technical Director of Westbat Intelligent Inspection Limited. The last one is Dr. Carmen Lee, Associate Professor in Department of Industrial and System Engineering from the Hong Kong Polytechnic University. I'm also pleased to have our Center Director and Executive Director of CAiRS, Professor Winkle Yung, to join us today. Thank you for joining us this morning. Before start, may I remind the audience that there will be a Q&A session after all parts of presentation. We have a special arrangement that system safety assessment. We are grateful to have Dr. Dhanada Mishra, Technical Director of Product Development at Westbat Intelligent Inspection Limited as our next speaker. Dr. Dhanada got his PhD from the University of Michigan in civil engineering materials. His research interests are in the field of non-destructive testing, different materials such as concrete, self-sensing and self-healing smart material, and AI-driven defect detection in built infrastructure. His topic is inspection and monitoring of built infrastructure system for safety and sustainability. Dr. Dhanada, please.
Thank you very much for that kind introduction. Welcome everybody. Good morning, good afternoon, depending where you are. My name is Dhanada Mishra. I'm very pleased to represent my company, a 4-year-old startup, Raspect Intelligence Inspection Limited. My topic is very different from the last presentation, if you were part of that webinar from University of Maryland. So I'll be talking more about built infrastructure systems rather than printed circuit boards and electronic components that were part of the earlier webinar. So we'll be looking at very large structures, the challenges we face in the maintenance, the safety issues, and most importantly, the sustainability issues, which has become one of the biggest challenges for humanity. So this is the brief outline of my talk. I will introduce the safety and sustainability challenges in the built infrastructure sector. Then I'll present the products that have been developed by Raspect for smart inspection, monitoring, and management using AI. The 2 products that I'll basically touch upon are facade inspection using automated unmanned aerial systems, and elevator system safety monitoring is an area which I'll briefly touch. It's a topic where we are collaborating and partnering with CAiRS and professors from PolyU and Sindler Company to come up with better online and continuous monitoring for predictive health maintenance. Next slide, please. So Raspect was founded in 2017 by young computer science graduate Harris Sun. He was at that time part of the Cathay Pacific Innovation Group, where he was bringing in some very novel ideas for inspection of aircraft fuselage. You can see a few pictures on the screen of the young team. And then he thought of utilizing the same approach of inspection to built infrastructure, particularly the tall buildings that Hong Kong is so famous for. So as a civil engineer, I found when I got introduced to Aspect this story very exciting and inspiring, because very often we tend to ignore our built infrastructure, particularly when it comes to concrete, which is my background, reinforced concrete structures and so on. We don't put much value like we do, let's say, in case of the aircraft fuselage. So when someone is trying to apply the same sort of approach and technology to inspection, defect detection, and safety monitoring of our built infrastructure, which are quite important in terms of their value to the society, I, as a civil engineer, definitely get very excited. Next slide, please. So Raspect has had a very successful 4-year journey. Next slide, please. And in this time, it has been supported by a number of very well-known investors, and it's been incubated by the Hong Kong Science and Technology Park, where we are sitting today for this webinar, and a number of other programs run by Hong Kong government to support startups. It started with the Alibaba Entrepreneurs Fund, Particle X, Mindworks, and Abacus. The basic mission of the company is basically to raise the safety level, the sustainability, and the cost effectiveness of operating our built infrastructure systems by utilizing AI and robotics technology. So we add value by bringing in predictive technology to manage the well-being at a lower cost and a higher efficiency. Next slide, please. As Raspect has progressed, its work has been recognized by a number of awards, both at the national and international level, including the most recent recognition by the Forbes magazine as the most exciting 100 young companies to watch in Asia. And we have had the good fortune to serve very well-known customers in and around Hong Kong, including HKSTP, Polytech University, MTR, Arup, all of the very famous names in Hong Kong, whose properties and assets we've had the chance to inspect. So coming back to building system safety, basically in Hong Kong, we have more than 21,000 buildings which are over 30 years old. And this number is going to keep increasing. Every year, almost 800 new buildings will get added to that figure. The number of buildings which are older than 50 years is around 8,000. It will be greater than 8,000 by 2030. And interestingly, by 2040, 1/3 of the people of Hong Kong, that's like a 2.5 million people, and 1/3 of buildings in Hong Kong, which will be around 20,000 buildings, would be more than 65 years old. So it's an aging society having to deal with a aging infrastructure. So it's a very big challenge. So some of the data here on the slide shows the numbers. Basically, we categorize old buildings into category 1 that requires emergency remedial works, category 2 that obvious defects are found, category 3 is where minor defects are found, and category 4 where no apparent defect, the building is in good condition. So this is from an investigation report that was done almost 10 years ago, which did a very quick inspection by building department of all of the buildings aged more than 50 years, and this is the distribution in various districts of Hong Kong. And this was the condition at that time, that number of buildings at that time that were in critical remedial emergency repair needs were 2. Then there were 1,000 buildings which had very obvious defects that also needed attention. So it's a fairly critical issue. We have at Raspec developed a large database of the building stock in Hong Kong, and that shows the distribution of the buildings with all of their metadata, such as the year of construction, the type of construction, the current occupation usage, the construction technology used, and so on. So we can map out the current situation with respect to particularly tall buildings in Hong Kong. So that's with regard to building safety issues, which motivate some of our work. The other key driver for Raspec's work is sustainability. And all of us know that most recent IPCC report was termed as Code Red for Humanity by the Secretary General of United Nations, because buildings are responsible for 40% of the carbon emissions, primarily because of the energy they consume or we use to run the buildings. Buildings also use 50% of extracted materials. By 2060, world's building stock is predicted to double. This is a big challenge, but it also presents a big opportunity, which is estimated at almost $24 trillion by 2030 to create energy efficient buildings. So obviously this becomes a big opportunity for companies like us. The Hong Kong's roadmap to net zero by 2050, which is the target set by Hong Kong government, and the national government's target of 2060 is to reduce the carbon emissions to net zero. So doing this for Hong Kong will primarily mean where 66% of the emissions come from electricity generation, 18% from transport, and rest from waste and other sources. And 90% of the electricity generated goes into building operations. That accounts for almost 65% of the emissions. So therefore, we have to have better monitoring of building operations in order to find ways to minimize the energy consumption and carbon emissions from our buildings. So the building carbon emissions compose of the embodied carbon that goes into the construction of the building in the materials, and the operational carbon, which is the main source, which is from the energy consumption. The typical building design life is 50 years, but what we can do through our work, through the inspection work, safety monitoring work of companies like Raspec, is to increase this service life and reduce the need for new buildings at frequent intervals. So that brings down the whole life carbon footprint of the existing building stock and helps us to achieve the net zero target. So that's one aspect of the inspection. And the other aspect is obviously reducing the energy consumption in the operations of the buildings. So now I'll move on to the actual products that Raspec has developed and offers in this domain. Basically, we have started with buildings. So this is a picture of our product roadmap. So from AI-driven building facade inspection, which covers reinforced concrete, cotton wall buildings, piping inspection. Most recently, we have come up with a product which focuses specifically on drainage piping systems. We are then moving on to the interior of the building, where the electrical and mechanical system inspection, the project that we are doing with CAiRS, which involves elevator monitoring, the elevator system functioning, chiller monitoring, which is a big part of the HVAC system and controls the energy consumption, escalator monitoring, and so on. Then we are moving into the broader infrastructure segment, where we are already doing POCs of road inspection and tunnel inspection, bridges and power lines, and so on. On the other hand, our roadmap also covers the pre-construction phase of the building construction sector. It covers the construction phase as well as the post-construction phase. And Hong Kong is a great place to prove some of the utility of our products before we go global with many of these services and products. This product portfolio can also be looked at as building management suite of products, and construction management suite of products, and infrastructure management suite of products. And we developed this with the vision that smart city management especially the urban infrastructure management, where the whole world is becoming increasingly urban. These are the products that we are going to need for more efficient, cost-effective, and safe management of our infrastructure. Basically, if we can divide our current major products into the ACE facade inspection, the ACE elevator monitoring. ACE stand basically for AI Cloud Engine, which is our cloud platform where we offer our products and handle all the big data for processing. So we use ACE for our facade product, for the elevator product, the chiller product, and eventually we are also developing the fire safety and indoor environmental monitoring products. And these products have integrations with building management systems, with IoT sensors, with digital twin and building information management system or BIM systems. The core technologies that underlie these products are the visual analysis, the AI infrared analysis, the AI vibration monitoring, and the AI magnetic monitoring. These are the 4 technologies that basically we use in building these products, and I'll try to quickly go through some of them. Next slide, please. Okay, so the visual analytics or visual analysis is basically based on the visual data that we collect of building facades, and this is typically done through use of unmanned aerial systems or drones. And this is part of the code of practice for mandatory building inspection promulgated by the Hong Kong government in 2012. Where every building which is more than 30 years old must be inspected once every 10 years at least. And the tall buildings of Hong Kong traditionally have been inspected through riding gondolas or using scaffolding, which is always unsafe, takes a lot of time, and can be very, very costly. And with our technology, use of drones and collection of the visual images, we are able to cover the entire facade or entire building envelope and then automatically analyze the data on our cloud platform using AI models to identify the most frequent and the most dangerous defects that you find on building envelopes. At the same time, we are able to collect infrared images of the envelope and detect other types of hidden defects that cannot be captured through visual images. And these defects can be water leakage, moisture problems, delaminations, debonding in concrete buildings, and so on. The vibration monitoring technology we mainly use for any kind of operating machines, whether it's a bearing, whether it's a pump or the motor that has a vibration characteristics that can be continuously monitored in real time, and any defects can be detected. Similarly, magnetic monitoring we apply in detecting the health status of things like the ropes, the cables that support elevators or cranes and things like that. So one of our major projects has been with one of the landmark buildings of Hong Kong, the ICC building, and here we have used most of our technologies and proven the concepts, starting with the cotton wall inspection and the thermal profile of the building using IR technique, and the elevator bearing monitoring using the vibration monitoring technique, the water pump bearing monitoring, and all of this. We have also developed a digital twin which helps to visualize the results and in real time allows the facility managers to monitor the performance of the systems and the building. We have a digital twin illustration here. I hope we can play the video. Yeah. So we have partners who help us in using our data to develop various visualization products, including digital twin and integration with BIM and so on and so forth. So with a digital twin like this, we can see the different layers of the structure, starting with the skin to the electrical to the mechanical systems and all of this, and we can see the operations of the different systems in real time. We can see the defects and the alerts when different sensors exceed their set limits and so on. So this becomes a very useful tool for facility managers to operate the building systems. So traditionally, digital twins have been used more for electrical and mechanical systems operation. But what we are doing as a company is to try to integrate the building envelope condition through routine inspection and the management of the building's physical and structural defect through structural health monitoring and so on is also being integrated into the digital twin of the system. So let me see if I can go to the next slide. Next slide, please. Okay, so now we will look at the facade inspection service that Raspec provides for particularly skyscrapers. This becomes a very important service. The workflow of this service, the facade inspection service, basically we collect the data through autonomous data harvesting using drones. Then there is data post-processing, the AI-powered data analytics using our cloud platform, then data visualization, and the big data predictive analytics. This is the workflow of the facade inspection product. And again, as I explained earlier, it uses both visual analysis and thermal analysis as the two main tools. And the visual camera and the thermal camera are carried by the drone. Next slide, please. To collect the data. One of the big difference between our approach and the conventional approach is that we cover the entire envelope of the building, whereas traditionally the surveyors tend to cover only some important parts and therefore tend to leave out much of the building envelope. So these are some of the deliverables from the inspection after the data has been processed. So we can come up with the defects, whether it's a crack or a spalling or a stain, or we have a database of almost 60 different types of defects, depending on whether it's a curtain wall building or reinforced concrete building or a tiled facade. And once all the visual data and the thermal data has been analyzed, our cloud platform can represent them in different forms, so the managers can plan the different actions. And they are also categorized in terms of their severity, whether they're a major defect or a moderate defect or a minor defect. Therefore, again, the repair and maintenance can be scheduled accordingly. And so this is a screenshot of our cloud platform. Next slide, please. So all of our products have the privacy protection and filtering of any privacy related information that is in the images, and we also comply with the relevant ISO standards. Next, please. Okay. I think we'll play this video to give you a small demo of how this facade inspection product works. And this is from a project which is very close by from this location in the Science Park. Very well-known project. I think the video has stopped. Okay.
事實上，本港亦都有地產商開始應用航拍。
Drone filming helps us to inspect high-rise buildings without the use of manpower and scaffolding, and therefore keeping our people on the ground rather than up in the air is a big save on safety. Secondly, it also helps us in the construction process in terms of speeding up our inspection, and that's a great help to not interrupt with our residents and our tenants in our buildings, so we can use drone technology to inspect the integrity of our buildings.
Yeah, our system also produces an automated report of the inspection. So all of the information about the defects, the likely origin, the cause, the consequence, and the suggested remedy is already included in the report. So I think I'll go to the end of the talk now, and we can take up the questions during discussions, and I can come back to some of the other products that I had planned to present. So one of them was the specific inspection requirement of drainage pipes during these COVID times for the safety and sanitation aspect of buildings. There was a requirement that we should have a specific tool and technique to inspect piping systems, which are often sites of leakage and spread of infection. Can we go to the next slides, please? And yeah, so we have successfully trialed this product in recent time, and this has been very effective in detecting automatically and very quickly all the defects in piping systems. So this is a video that shows, very quick 1 minute video, yeah, that shows how this is done. So we fly the drone using a crane jib, which is supported from the roof of the building, and we capture the video, and our AI model is able to catch all the defects in the piping system without anybody having to climb the building or take any kind of risk. So this is our latest innovation. So last portion of the talk was about the elevator inspection, and I will skip it for now because time is almost up, and we'll come back to it if it comes up during the question and answer session. Let me just go to the last slide if possible. Can you? Please, next slide, please. If you can go to the last end of the presentation. Yeah. So that's our team, and thank you very much for your attention. This is the young Raspect team. We work out of Inno Center in Kowloon Town, and I thank you for the opportunity. Thank Professor Yoon, and thanks CAiRS for this opportunity to present our work. Thank you. Thank you very much.
Thank you, Dr. Dhanada, for sharing your experience. Kindly remind our participants to scan the QR code if you have any questions that would like to ask Dr. Dhanada. Let's invite our guest speaker, Dr. Kamani. Associate Professor in Department of Industrial and System Engineering of the Hong Kong Polytechnic University. Her topic is Big Data Analysis for Predictive Maintenance Strategy. Dr. Lee, please.
Okay, good morning, all of you. So maybe we go to the power slide. So my topic today is about for the big data analytics for the predictive maintenance strategies. So I think most of you know quite well about big data, but just let me to use around 1 minute just to talk about for the big data. So as we know that for the big data is related to 4V, and it's not only a matter of volumes increase of the collected data, because most of us may be more concerned about for the volume. Especially right now, we have a lot of sensor IoT device, then it can quickly increase the volume. But on the other hand, we cannot ignore is about the main point is about the values, because most of the decisions is made based on the value data. And it cannot deny that throughout the life cycle of the products, when we collect those data, some of the data may be very valuable, but some of them may be just, I can say that, for the normal operations of the data. So apart from that, as right now we have a lot of variety of data. The data can be same as Tahanda's what you show here is about the image, not necessarily just text data. But on the other hand, maybe there's different types of social medias, and for example, we may have the videos or the sound data. So how to extract those data such that we can make use of those data that can help us to do some predictive maintenance. And here you can see the workflow. Maybe you can realize that, okay, when we collect all these big data, we may have different techniques to handle those data. For example, we can process those data with some statistical method. Same as the first speaker mentioned about that, okay, we can use some advanced statistical techniques. And on the other hand, maybe right now we are more concerned about data-driven models. So for the data-driven models, then we may concern for the data mining techniques such as classifications, also clustering, associations, and regressions. So these are the typical approach that we use in our data minings. And apart from all these data, I can say that we cannot ignore is about experience. Sometimes the technical staff may give you some hints about how to make use of those data. And when we have those informations, then we can conduct the predictive maintenance. And through the modeling, then we can realize that what is the remaining useful life, and also we can do some analysis about degradations. So, for example, through the use of the IoT and also the sensor device, we can realize that the conditions of the components. And when we can predict the life cycles of these key components, roughly we can estimate that the system life cycles. And also, when we do the maintenance, we also need to achieve certain our objective. As we know that for the critical components, it may cause the fatal effect for some of the situations. So that's why we put more emphasis on it. And on the other hand, that through the optimizations of the predictive models, then we can make use of some numerical method and analysis method.
What are the three maintenance strategies that are commonly used to manage assets?
Short videos
and how do they differ?
The main difference about
the first is referred to as reactive or corrective maintenance. The second is known as preventive maintenance. And the third is predictive maintenance. Let's take a look at how they differ. With reactive maintenance, an organization does nothing until the asset fails, and then responds. With preventive maintenance, an organization performs tasks on regular intervals until failure occurs. With predictive maintenance, the tasks vary depending on the age and changing condition of the asset over time. At particular points along the curve, certain leading indicators of failure can be detected and addressed proactively. With reactive maintenance, an organization may not be able to achieve the full service life of the asset. When an asset failure occurs early, some of the potential life of the asset is lost. With preventive and predictive maintenance, the organization is able to potentially achieve the full service life using the proactive planning methods, which vary in their mitigation effects. An organization will apply one of the three maintenance strategies depending on its future orientation and attitude to managing failures. With reactive maintenance, there is no attempt to gain insight into the future. Issues are managed in the here and now. With preventive and predictive maintenance, an attempt is made to look into the future. The difference, however, is that preventive maintenance seeks clarity only until the next planned maintenance task. Predictive maintenance, however, tries to anticipate the eventual failure of the asset and works backwards from that event. There can be a significant monetary impact of the three maintenance approaches. Reactive maintenance is cheaper in the short term, but more expensive in the long term, as the organization incurs additional costs from a shorter asset life. Preventive maintenance incurs fixed costs at fixed intervals, which may not reflect the changing condition of the asset. Predictive maintenance incurs more upfront costs, such as the acquisition of diagnostic equipment and staff training. It is, however, aligned most closely to the changing condition of the asset. Both preventive and predictive maintenance are able to mitigate the failure cost through their proactive steps over the life of the asset. Finally, maintenance activities can also be plotted onto a deterioration curve. The graded color scheme reveals the changing risk profile of the asset being maintained. With reactive maintenance, no action is taken before asset failure, and the organization can be caught off guard. Preventive maintenance follows a fixed interval approach until the asset fails. Predictive maintenance, on the other hand, applies variable intervals of maintenance as the asset condition changes. At the end of the day, each asset needs to be aligned to an appropriate maintenance strategy. These decisions are based on many factors, including the criticality of the assets, regulatory requirements, and the availability of diagnostic technologies to reveal concealed condition.
Okay, so when we through the videos, I think you can roughly to realize that, okay, the importance of predictive maintenance. And also when we do the predictive maintenance in our maintenance policies, so first of all, maybe we consider about the criticality of the failures. So in some critical assets, they may have a high rank in priority formulas. And also in our strategies, we try to think about that, okay, what is the next machine breakdown and what is the random errors? And indeed, for the sensory data, it can give us the monitoring about the conditions of those devices. And for the current operation status, for example, if in some cases they find that it's some abnormal performance, then we can realize that we can ask the technician staff to help to identify what is the failure situations and what is the failure models of the machines. And with the reliabilities, and then the system must provide correct measures. And for us, we can see that for the performance in the predictions in those areas for the visible and also foreseeable machines failures, and also somehow we also think about for the condition-based monitoring. So another major things that we consider about for the time series is that what times that we can carry out for the maintenance and repair operations. So surely the ideal case is that we want to have the zero tolerance of the equipment failures. But when we have all these informations, then for the data relevance and how to extract those informations can help to let us to have the maintenance decisions. So that's why in general, most of the researchers tends to have the knowledge objective-oriented strategies. That is that they try to make use of the implicit knowledge and then from collaborations of sensory informations and then to make it to be more explicit and also maximize the production efficiency. So for the next slide, you can see here is about for the predictive maintenance models in big data platforms. So for the ideologies of the predictive maintenance is to create the transparency of the machine's conditions, and also for the utilizations of available information for the maintenance decisions. So in the figure, you can see that, okay, for the big data platform, we try to design for the closer integrations of data acquisitions and also how to set up the maintenance support systems. And for the flow that we think about for the diagnostic aspect and also the prognostic modelings in the predictive maintenance. For the case examples that later we will show here about for the semiconductor situations. So in the big data platforms, so we can try to think about the operations of the maintenance decision support systems. And also for the operating data, for example, we will have the vibration data. Sometimes we have the heat sensor data or pressure sensor data. So for those sensor informations, then come up with the big data base and to make use of some big data techniques such as the MapReduce techniques, then we can help to extract, transform, and load those data in a timely manner. So based on some data algorithms, then we can realize that for the predictive maintenance, how to carry out. So for the common practice for the AI techniques, I think most of us, we know that, okay, we would like to set up for the knowledge-based systems. We hope that through extractions of some rules or algorithms that together with the human intelligence, then we can have the some insights about for those informations. And also we can have the machine learning techniques and data mining techniques. For this figure, I think I don't need to go through in detail because as the first speaker, I think he go in depth about for the prognostic and diagnostic process. But just to give you a full pictures about, so when we realize that they have some fault, and then it's the times to have the prognostic, and then we think about for remaining useful life, and that is the diagnosis about what is the failures time that may come. So for here, you can see that for some diagnostic or prognostic process procedures, so when we have different informations, we base on the past operation documents and some condition records. So for the diagnosis, we can think about for the machine health conditions, and then for this figure, we realize that for diagnosis process, it determines how the system has degraded. And also for the cause and natures of such degradation conditions, then the faults are detected and isolations and identified for the diagnostic record. And for the fault possibilities, so they can compute the potential failure patterns, and so the diagnosis process can follow the operations. And also from the effect and also find out the failure cause and do further analysis. So in the system levels, then we will also think about that how critical components that may affect the whole systems. So as we know that for the system, it made up of the different components. And so when we predict the remaining useful life, we estimate the useful performance life cycles of the whole systems, and such that we come up with the output as our prognostic result, and also we can upgrade the prognostic history. So in this flow chart, it can help to look at the maintenance decision support systems. So you can see that for the extractions of those data, then through the identifications as one of the diagnosis. So we may think about for the strategies here. So for the strategies, you can see that the small table there. So we have some situations that we try to classify into two areas, two dimensions, about the frequency and also the downtime. So for the frequency, we talk about for the low or mediums high, and for the time is also same. And when we look at the, sorry, I need to go for the next slide. Yeah, so for the frequency and downtime, as I mentioned, these two dimensions. So when we look at those strategies, sometimes we may find that in certain cases, maybe we prefer to operate to failures. So because of the economic concern, or also think about the criticality of those components may not be as the high priorities. But at the same time, we may think about for the fixed time maintenance. So for example, if in case the frequency is mediums or downtime is mediums, but on the other hand, we also try to classify, even for the fixed time maintenance, okay, we have different types of the categories. And surely for those frequency which is high, and also when we think about for the frequency is low, then we would like to make use of the conditional-based maintenance. So here is the generals about for the strategies that we adopt based on these two dimensions. So when we look at these cases, so maybe you say, okay, we already have the table, why bother that to make use of the AI techniques? But on the other hand, somehow we always have the fuzziness of these high or low or mediums, because sometimes it's very difficult to set the boundary of those data. So we try to make use of the fuzzy logic for diagnosis for the machine failures. And we make use of the fuzzy inference system editors, and then we come up with the fuzzy rules such that it can be more systematic. And on the other hand, for the diagnosis, we may think about how to visualize, because in certain cases, when we see the data, there's a lot of data, but how to visualize and make us to realize that, okay, is the time, is the values that fall in the range that we should carry out certain types of the maintenance. So it gives us better pictures about the decisions that we should make. Sorry. So for the slide here, I just extract some of the faults that it can be detected by semiconductor machines. So you can see that, okay, I highlight in yellow color that, okay, what type of errors that may happen in the semiconductor machines, and it comes up to the conditional-based monitoring. Because we realize that maybe through the machines, they have a lot of sensor, and even for the errors that maybe they have many errors that can pump up. So we need to classify them and realize that which strategies that we should make with those stated errors. So, and also here is come up with the figures about for the multidimensional deep neural network. I think most of it we will think about in the past, we used artificial neural network. But right now, then we may try to make use of the deep learnings. So for the deep learning, here is come up with the concept that for the multidimensional deep neural network, that it can have the bidirectional LSTM, so for the long-term, short-term memories. And then it have the recurrent, the gauge recurrent unit channels to extract the multidimensional features. So indeed, you can see that most likely when we collect the data, we have the vibration signals. So those signals, we need to do some figure out and then to have the degradation features. After that, when we come with the multidimensional deep neural network, then we have the concatations, and then we can come up with the regressions layer. And so we can predict the remaining useful life. And for the details of the research, I think I don't go in details because it has been found in the paper. Okay, maybe I just use a few minutes to round up because of the time issues. So for the predictive tasks in the, when we realize that for the predictive tasks in the multi-dimensions deep neural networks, so we can see that for the health conditions assessments, so surely to recap about for this morning's seminars, so our main goal surely is to monitor the machine's performance and then the machine's component degradations and considerable maintenance actions that we try to carry out and then figure out what is the components that can do the replacement. Sometimes we realize that it's very difficult to repair, but maybe the easier way is for the replacement. And for the abnormal detections that through the systems, we can, based on the past historical patterns, and we realize that, okay, what is normal and abnormal. And also, on the other hand, we think about that to make use of the machine learning techniques to have the current and normal conditions for identifying the abnormalities. So regarding for the remaining useful life assessments, so we also have think about for the estimations of the monitorings of the useful life by sensory informations. So as I think the HANA's companies, they has a lot of the sensory and also some device to identify the useful life, and also the main issue is that we have to forecasting and then projection. And as we know that for the maintenance very important, how can we make use of the data-driven scheduling rather than just periodic maintenance? Okay, so through these predictions, then we can realize that and emphasize some proactive maintenance, not so reactive only when it breaks down, because once it breaks down, it comes up with a lot of problems. Even you want to have replacement, you realize that you need to wait for a long time for the spare part, and then it also keep the system down for a long period. So this is the concern. And for the future direction, surely I think it's a good platform for the CAiRS to have the collaborations with the industrial expertise and scholars that it can involve both scientists and also for the industrial experience and also knowledge that about how to set up the data analytics for maintenance strategies. And on the other hand, that we also realize that for the real-time monitoring is also another strategies that we should further follow up. And when we have those lots of data, in some cases also consortiums, they also think about for the open data platforms. Okay, so for the implementations of the cyber physical systems, so it can synthesis for the data for the wireless sensor network, and also we have the risk assessment and impact evaluations for the further machines failures. So I think all these things come up with our future work, and then we do look forward for the next seminars that we can talk with one another and see whether we have more possible solutions.
Thank you, Dr. Kamali, for your remarkable presentation. Kindly remind our participants to scan the QR code if you have any questions that would like to ask Dr. Lee. Thank you for all the speakers and their inspirational sharing. I hope that all of you will find this sharing inspiring and exciting. In the following time, I would like to start Q&A session. Let's see what our participant is asking. The first question is for Dr. Danada. When using digital twin to predict the health of a building, does it require continuous data feeding, or it can just tell by simulation?
We generally don't do continuous monitoring of the building's health in terms of the physical condition, but we continuously collect data of the systems. But if you are talking about the building itself, then we propose that there should be a periodic inspection regime. And our system, which is very inexpensive and very efficient and easy to conduct, can carry out the building inspection, let's say every 6 months or every 1 year, and also establish a baseline of the building in terms of its digital twin, and then compare it with subsequent inspection result to see what changes have taken place in terms of new defects or new features that have come up on the building. So accordingly you can take decisions. So that is our proposal, but generally it is not done in conventional practice, but we hope with the new technology availability and the easier approach to handle the big data using AI approach, it will become a new practice to conduct more frequent inspections of the building.
Thank you, Dr. Danada. And the second question I would like to ask Dr. Lee. Usually, maintenance is done before failure really happens. Does it affect the collection of data for prognostic prediction?
Yeah, I think when we collect those data, surely for the prognostic, we want to first find out the faults first, rather than just failures. So before the failures, we may maybe have some symptoms that we can realize. And through the collections of those data, we can realize that maybe through the curve that we can see that they have a certain surge up for a certain area or peak. So surely we need to monitoring, because sometimes it cannot deny that in certain situations it may be the false alarm. So we need to identify it is the challenge and difficulty to do the maintenance. We don't want to interrupt the operation, but on the other hand, we would like to predict correctly about which one is the true alarm and then the false alarm.
Thank you. And the last question is for Dr. Lee. What is the potential cost for switching from conventional maintenance strategy to MDSS, such as installation of sensor, network, storage, etc.?
Indeed, in the setup, I think the cost is about for the developments and also the way to collect your data and analyze those data. And also for the human resources aspect, we need those expertise. So compare with that, okay, we can let them to failures and then it breakdowns, then surely we need to invest. But on the other hand, we need to realize that if that part is critical or even it lead to the fatal case, then we need to invest in those specific cases.
Thank you. Thank you all guest speakers for sharing your specialized concept on advanced in predictive maintenance and system safety assessment. Ladies and gentlemen, at this moment, we are very honored to have Professor Winkle Yong, Center Director and Executive Director of CAiRS, to be here with us today to offer a closing remarks before we end this webinar. Professor Yong, please.
Yes, thank you, Winkle. Do we have online questions from the Q&A QR code? Maybe while I'm doing the closing remark, you can look at the online, whether there's any Q&A questions from scanning the QR code, right? Now, sort of closing, but actually I want to echo what our speakers talked to us this morning. We have 3 or 4 speakers this morning, speakers from University of Maryland and from Purdue and from the industry. Now, all in all, we also mentioned about diagnostics and prognostics. And that should give the audience a sense the relationship between the two, right? Now, of course, at the end of the day, we will try to use what we call PHM, Prognostic Health Management, to predict or to do predictive maintenance. Now, predictive maintenance, like what Dr. Kamini mentioned in one of the slides, that is very, very effective in terms of saving costs, in terms of putting up quality and reliability, much more than corrective maintenance, much more than preventive maintenance. Now, predictive maintenance is the way to go, particularly if you want to make a brand for your products or make a brand for your service, okay? Now, but before we do prognostics, diagnostic is a must, right? Because we have to make sure we know what we classify as faults or even anomaly, right? We would prefer to say anomaly or use the term anomaly rather than failure, you know? Sometimes even more than a fault, you know, because before failure happens, it may be a fault before fault happen, it may be something abnormal. We call it anomaly, right? Now, how we relate this anomaly to health index in each of the applications in terms of buildings or systems or components, that is something what we call domain knowledge, right? It should be different in different applications, right? When you talk about electronic components, all those manufacturers, they have more domain knowledge than us, how to relate anomaly to some of the process phenomenon, some of the process parameters, like building, they may be totally different, right? Well, to add on that, that also gave us a sense that prognostics and diagnostic can be equally applied in different industry, right? You name it, like Dr. Takada told us the application in buildings, right? And also our colleagues from University of Maryland, they also have some sort of applications. And Dr. Kamani also mentioned some of the other application as well. So all in all, well, diagnostic is the first step, and then it brings forward to prognostics. And hopefully, CAiRS is here, also working on two legs. One is to use prognostic and diagnostic to help industry to uphold their reliability and safety, or even improve them. But on the other hand, we also need some domain knowledge, and this domain knowledge has to be from the industry, right? And also one very important aspect from Dr. Kamani is on data. We have a lot of data. We have 28 collaborators at the moment for CAiRS. A lot of collaborators told us that they have data, but two things. Some of them are noise. How do we differentiate whether they are useful data or just noise data? That is very important. That's one. And even they are not noise, are they useful enough that we can do data clustering, data patterning, data inferencing? That's another matter. So there's a lot of research at the back to do this kind of prognostic and diagnostic. And hopefully, if the public audience, if you see a need, please do come to visit our website, CAiRS website. Hopefully, we can help. And from time to time, actually, this morning webinar is one of many webinars we have held in the past. And on every Wednesday, we also have public lecture. All in all, try to bring up the awareness of public audience, particularly from those from the industry, that diagnostic and prognostics are very good methodologies to help to bring up your reliability and safety level. So with that, this is my closing remark. And once again, I thank you, Dr. Takanta and Dr. Kamani. Yeah, I hand over back the time to Dr. Wingbo Lee.
Okay, since we have some time left, maybe we can ask Dr. Lee for a few more questions. There's some new questions pop up. For Dr. Lee, is that a fair assumption that predictive maintenance equal to labor reduction, hence a right expectation on maintenance cost reduction?
Okay, so it's very practical problems then. We always want to reduce some costs, especially labor costs. But actually, from my perspective, is that when we do the predictive maintenance, we can keep the system to continuous and work. And for example, in some public transport, we know that the reputation, reliable service is very important. Right, so it's not just for reducing the cost. And on the other hand, is that to maintain the reputations of the product and the systems is another concern that maybe is not easy to be quantified. Yeah, but in case you can imagine that if the system fail and then it affect the customer satisfactions and then the loyalty, then it may be another cost that we need to pay.
Okay, and another question is for on the page 14 of the PPT, how the bidirectional LSTM model can predict RUL.
Yeah, sorry for that. Because of the time overrun, that for this multidimensional deep neural network, that because indeed for the bidirectional long-term short-term memories, then we have also have some situation is that okay, we can capture those data and then can figure out that the degradation patterns. And for those degradation patterns, then we realize that through the statistical models, I can say, then we also can realize that, okay, what is the remaining useful life for that components.
Thank you. Again, thank you to all our guests and participants for joining us today, and most heartfelt appreciation to all our speakers, technical support, and supporting organization for the webinar. I hope all you find the webinar beneficial and valuable throughout the webinar on the topic of advance in predictive maintenance and system safety assessment. I wish you all a nice day. Thank you.
Thank you very much.